So I'm very grateful for the opportunity to speak here and present my work. So I was asked to give sort of part of a review talk on the connection of gravity and string theory. And then I will slowly diverge into newer subjects like BCJ and CHY relations. So the work I'll be presenting is work together with a lot of people, actually. But most recent, Christian Bådsgaard and Paul Damgaard and Pierre Van Hove. So since the very early days of researching quantum gravity, it's pretty clear that this is not a standard kind of problem. It's actually quite complicated, and usually you lead to very tedious calculations. So my first approach when I studied the subject was actually to study the Einstein-Hilbert action, and there's a very nice book by Feynman, his lectures on quantum gravity, which is sort of a nice account of how he thinks about things. And the basic thing he does is he rederives the Einstein-Hilbert action from the first principle. And the way he proceeds is just expand the metric around the perturbation. But this is extremely ugly, and I mean, it's very hard to believe that at that level in the 50s, where computers were not so easy to get by and stuff, that one could at all compute something. So in this theory, there's like no manifest simplifications. You just expand everything out. It's ugly. It turns out to be a non-renormalizable theory, as Toft and Veltman shows. And if you read their paper carefully, you can see in the last paragraph they write they really exhausted after investigating this problem. And the reason why it's so complicated is this explosion of vertices. So the first vertex one encounters is actually nicely worked out by Shannon. And it is this term here. So it doesn't look so bad, but each of these are permutation sums, and there's lots of symmetry factors. So this is just the 3-point vertex, so the building block. That has 45 terms plus symmetrization. That means 100 terms in contractions. As you move to the 4-point interaction, you grow a factor of 10, so it's like more like 500, 1,000 terms, and so forth. So it's like you want to compute a 5-point amplitude. This is just so complicated. And we saw some of this in Henrik's talk yesterday. The good thing is that today we actually have a much better understanding of quantum gravity. So we can understand it now, the Einstein-Hilbert action, as a first term in an effective series of higher derivative corrections. And this is mainly due to an idea by Weinberg in 1979. And this was nicely worked out by Donahue. And through this, we can make meaningful predictions. And Pierre will talk about this later or tomorrow. And we can use a lot of nice techniques in this. We can use these Yang-Mills techniques like recursion, unitarity, spinor helicity, and then we can recycle Yang-Mills amplitudes into gravity. And this is through a string connection. And through this, we have actually been able to prove stuff like if n equals 8 supergravity is finite. And here I refer to Byrne and Davis talks later. So the topic of my talk will actually be just to consider string theory as sort of a useful laboratory for considering Feynman, or the way we see things in gravity or in Yang-Mills through KLT, the way we see things through Feynman diagrams, and sort of compare what string theory tells us, because there's a lot we can learn from just comparing these two sides. And the first thing one sees is that in string theory, we often compute very simple objects, while on the Feynman graph side, we have to do a lot of permutations and combinatorics to get the same. So I'll try if I can make this point more precise later. One of the important features of string theory is actually be the introduction of the notion of color ordering. So notice in Yang-Mills, when we talk about helicity amplitudes, we never almost mention the color factors because they're always put outside like a trace. In the Feynman rules, we actually have to work hard to get this. So we have to put in these vertex rules that have color in them, and then we have to work out these contractions of the color indices. And we will see if we do a Feynman expansion that it gives you a trace. But it's always already telling us that string theory can do something that field theory is very hidden in field theory. So to do gravity amplitude, we start with this object here. So this has already been simplified a bit. I put the vertices are hidden in the f and the g function. There's like two variables, there's the c and the c bars, and we have to integrate over both. Then we have all the insertions here. So there will be some that are connected to, there's a gauge fixing here, so one leg is put to 0 and 1. That's these two legs, and the rest are sort of insertions between legs in this set, IJ set. And the amazing thing is actually that we can take these vertex operators and separate them into the part that goes with the bar vertices and the ones that goes with the unbarred vertices. That means we can take the closed string and kind of see it as an open string times open prime string. This is not necessarily in the way it's derived left-right symmetric, so this can be quite a different object from this. But it allows us to write this formula down where we see the closed string as sort of a sum over phases times Yang-Mills amplitudes. And this is basically directly what's in the Kawai-Levellin tie paper. The problem in this formula is actually to work out the phase factor, which is non-trivial. I mean, on the world sheet, one has to do a lot of manipulations to see this coming out right, and then in the end you have to combine all these phase factors to get this. But I'll show you how to compute this very simply. And these things here, you can just replace Yang-Mills amplitudes. The thing is, and that's interesting, this phase factor depends on the ordering in these amplitudes. So this will change depending on what the order is here, and there's some orders that are nicer than others. In the link in string theory, we kind of we seem to link the individual Feynman diagrams in a sort of non-simple way. So when we write out the string theory integral here and we make the KLC split, we can't really any longer see the Feynman diagrams. And this is exemplified when we try to work this out at the Lagrangian level. I'm hoping to see Rutger's talk because I think he will speak of something related to what Holm has been trying to do. But there's some old papers here by Byrne and Grant and Ananda Tyson and latest by Holm about how you can sort of factorize gravity at the Lagrangian level and try to see it really as a double field theory. If you want to be explicit, one goes to Byrne's paper and see these two formulas. And you see these momentum factors here. These are actually something that we have later phrased as a momentum kernel because it's related to the way BCJ works. So these are these exponential polynomials that now are taken in the limit of alpha prime going to 0. So the exponential becomes just a polynomial in S. And they come outside and sit here. And the interesting thing about how this works is that you do get quite bulky expressions because you have to sum over these permutations here, and this sum just grows. Since there's no rule for how to pick the Yang-Mills amplitudes, the way the canonical way KLT works yield a way that is really not manifest crossing symmetric. And you see in the amplitudes that you have that the S factor is put in to cancel double poles. So for instance, you have a 1-2 pair here. That has to cancel that pole that comes from the 2-1 pair here. So when the sum works, it knows about this. And I think all these things come very clear when you look at it from string theory. And in the old perspective, one curious thing that was always noted was that the KLT relation work independently of the external polarizations. So that points toward it being somehow a more general thing. So Henrik told us about the kinematic structure in Yang-Mills. So basically, we can take Yang-Mills and we can write it in this very curious form where we separate color and kinematic and we write denominators which are basically just like phi cubed denominators. So we have this sum over I, which is like different phi cubed denominators. And for each of those, we have a numerator factor and a color factor. And the color factor, we can see very easily is a trace of just FABCs. But the numerator factor is kinematic, so there we have to work in order to work it out. And the BCJ conjecture is really that The same kind of relation that holds for the C, which is a Lie algebra, should also hold for the n's. And we have promised that there will be some choice of n's that actually work if the BCDA is supposed to work. And this immediately gives relations between the amplitudes. So in the old days, these things were considered a little bit curious that they would work. But you can see that you take an amplitude 1, 3, 2, 4, and you multiply with this factor times this amplitude, you end up having this. Now, if you go to the BCDA, you can derive stuff at 5 point. So the relations look like this. So they have like S, and then you have an A5, 1, 3, 4, 2, 5, times this S, and you have this amplitude, and so forth, and you get a 0. And it's very easy to see from this that it points towards there being a basis of n minus 3 factorial amplitudes at any point order, for which basically is the basic ones, the ones you can't compute from the BCDA. If you go above this number, you can find relations like BCDA or the KK relations that link those together. And also it points toward a very nice way, a new way to do gravity, where basically instead of putting a color factor, you put an extra factor of the n's. And it was shown by Bjerrum, and especially in this paper, Bjerrum, Dennen, Wang, and Kiermaier, how this construction would have to work once Yang-Mills BCDA relations were in place. And this is the origin of this phrase of the double copy gravity from Yang-Mills. And we've already seen Johansen's talk and Oshirov's talk on, I think, Friday. It will be interesting to follow. So what can string theory tell us here? So the generic expression for doing a superstring Gluon amplitude is this one. You can see it in Green-Schwarz-Witten. So it consists of various factors. The interesting part is actually here. This is where the kinematic information comes in. So we have the epsilons. These are just the epsilons of the external legs. We have the epsilon dotted with the k's. And we have some kinematic information here sitting in what's known as the Koper-Nielsen factor. Down here is an interesting fact that will be important later in this CHY formulation, that this subtraction here is very important. It's between the bosonic pole that sits here and the fermionic pole here. And actually, the kind of cancellations that happens between those two terms allows us to write this expression totally in terms of single pole terms like Zij. And this is what allows us to later take on global residue theorems and stuff like that and derive CHY. For monodromy, actually, the only thing important is this factor up here, the Koper-Nielsen factor. So in this sits the insertions, and we have all of them in this product sum here. And it's to the power of alpha prime to the Sij. Whenever an insertion, whenever you have an integration on the volume that's ordered, and the ordering changes, like you change from one volume to another, you get a sign of, you flip the sign here, and that introduces a phase in the alpha prime Sij. That's the origin behind the KLT kernel, and that's what we need for deriving it. So how do we derive something like monodromy in string theory? Well, the thing is to just look at the simplest example you can actually come about, and that's the scalar. So you can compute a scalar from just looking at this following integral. So if you have an ordering of leg 1, 3, 2, 3, and 4, and you pick only leg 3 as the leg that's not gauge fixed, and the rest are gauge fixed at infinity, at 1, and at 0. This is the expression you have to compute the amplitude. So you see it's a very simple integral. It's just an integral in x to the alpha prime k1, k2, and 1 minus x to the alpha prime k2 dot k3. And now we can do all the orderings at 4 point. So you see we have those integrals here, and they are ordered differently on the real axis. So they lie in different volumes, so to speak, one-dimensional volumes. Now the thing is, if we look at an integral that goes from 1 to infinity, so this integral here, we can actually flip it across the axis over here. So that introduces a phase shift, both from 1 to 0 and from 0 to minus infinity. That's the two phase shifts. And now BCJ and KK just follows from this argumentation. So for each flip, there's a real part and there's an imaginary part. For the real part, we simply just link the original amplitude to a representation where the legs have been flipped across. So in this case, we are flipping across the ordering. So here 3 is on the other side of 2, and here 2 is on the other side of 3. So we take amplitudes that has 3 on the other side of 2 to amplitudes that have 2 on the other side of 3, and compute this phase relation. And the BCJ relations follows from the fact that we can also do an imaginary part. And there's no amplitude because it just, the phase should be 0. So that links these two directly. And through that reduction, we can see that string theory tells us this will be a sine alpha prime. Field theory tells us it will just be an S over a T or a T over a U. And these basically are trivial to derive once you've seen this. So this gives a very nice link to the BCJ relations by Bjerrum, Krasko, and Johansen. And it immediately extends to higher point. So we just look at amplitudes that has sets on either side of 1. So we have an alpha set, a beta set. And then we try to link that through the flip. So this amplitude here is linked to amplitudes that sits on the other side, where 1 is the first leg. And the BCJ relations are then the amplitudes where 1 is fixed and n is fixed, and where all amplitudes are lying either in an alpha or beta set. Yeah.
Historical question. If it's so simple from the string theory point of view, why was it understood only later?
It's a good question. I mean, it is sort of present in the KLT paper, but it is actually not so simple in the string theory to sort of work it out. I mean, there's some details you have to, for instance, for the gluon, I mean, it's exponential. You have to expand it. And you have to have the idea that something like this would work. But it could well have been discovered, say, in the 70s by, there's some very nice notes by Dusenko. I don't know if you know them. 100-page notes in French. And I mean, he's very close to some of these things, but he doesn't say it. I mean, he uses stuff that looks very close. So these are just the expressions you can derive. For gravity now, it means we have a unique way of rearranging the KLT relations. So we wrote this up for the 4-point, where we take the 1 to 4 leg, and we write it with an S and 2 Yang-Mills amplitudes. So now we can use one of the BCJ relations to basically take this one. We see this is the same as this one if we cycle it once. So we can write it as this one. And if we do that, we can derive formulas like this. So we really see Yang-Mills squared coming in. So the way that monodromy works allows us to see the squares directly. It's, of course, not as beautiful as the numerator way of writing a double copy, but it gives us a very sort of hands-on way of rewriting gravity. And this continues even at 5-point, where we can write up expressions like this from the monodromy. So it turns out that the important thing to consider is actually this momentum S kernel. So these are the S factors, the S polynomial you put into the KLT. And it takes this form, and it was actually derived in Copenhagen together with Bo Feng. And it expresses the phase difference between the orderings in the set. And it has very nice properties, like you can flip the I set and the J set, and the momentum kernel stays the same. So it's a very symmetric object, but there's some choice in involving picking this T up here. But it also gives us a very nice relations, and this is how it was derived. It was derived as the object, the matrix, that would take the Yang-Mills amplitude in the n-3 factorial basis and actually map it to 0. And therefore, it's named momentum kernel as somehow an annihilator of the amplitude. In string theory, and this is actually this is where I think why it wasn't discovered. I mean, this is the kind of stuff you have to do. So in string theory, when you look at the closed string, you have two momentum kernels like this in place. You have the Yang-Mills amplitudes, and you have to then, on this complex contour, this double complex contour of Z and Z bar, work out how these contours can be separated in the right way. This is what KLT did, but they didn't explain it very explicitly. And if you do it in a way sort of more hands-on, you can actually see that the way they derive is not unique. There's many ways of deriving KLT and making the separation, and some are nicer than others. And once you put everything in the momentum kernel basis, it becomes much easier. So for instance, this form is possible from string theory. This is not the standard KLT form, but it's another one. So it keeps two legs fixed, so I and N. So it orders this amplitude backwards and this one forwards. And the two sets gamma and beta are just, we sum over all permutations here. And the momentum kernel is just this. So this is an N minus 2 leg crossing symmetric gravity amplitude. The only thing it's missing is also symmetrization in N and 1. But we have some expressions in the paper that are even more symmetric with 1. So. And if you go to string theory, there's no problem in extending the S kernel was actually derived from the BCJ at field theory level and then also found in string theory. So it's not a problem to go to the string theory version where you just replace the dot products with a sine function. And you see that string theory have relations like this, like an S kernel in string theory type of annihilation relation. And as Henrik pointed out, in the same paper, we also present some way of generating BCJ numerators from KLT, especially using this momentum kernel expression. So this gives a lot of insight in how we compute. So string theory, I mean, just as a laboratory, is actually a very neat way to trivialize certain simplifications. It has given us things like color ordering and monodromy relations that gives directly the reduction of the basis of amplitude. It also gives us Kervailevan tie, and it provides us with factorization limits, which I think is also important. I mean, a lot of these soft limits come out very easily once looked at from the string theory point of view. And there's a lot of literature on that.
Is there an explanation from string theory point of view why there is n-3 factorial of the equivalent numbers?
It's actually quite simple. So in the Copenhagen gauge fixing, you pick 3 points. So set 0, 0, and set n infinity. So you have n point, but you gauge fix 3. That's the number. And the factorial is just that the legs that are not gauge fixed, you can compute over. So in 2003, it was suggested by Cachaso that Hay and Juan, that one can actually compute amplitudes via this formula here. So it's a very surprising formula from the point of view of field theory, and it's actually, as it turns out, not so surprising from the point of view of string theory. So the formula relies on a lot of observations that are known in string theory, in field theory and in string theory. Basically, the trace factor here, it comes in for gluons. So when S is 1, you put a trace factor in. When S is 2, the trace factor goes away, and we have gravity, so the tachyon squares to a determinant. When S is 0, we get this squared, so we get like a double-colored scalar, and the cyclic factor squares. And the delta function we have here, well, this is there. This is the scattering equations. And this integration we have up here is very close to what you would think of as a Möbius, a Copenhagen gauge fixing. So we thought it would be interesting to understand this better, how we could maybe see some of these ideas from string theory. So for the endpoint scalar amplitude, Dole and Goddard worked out the relations, and the amplitudes are reduced once you leave out the tachyon and the trace. Then you just get this factor squared. So basically the integration is just this cyclic factor times the gauge fixing plus an integration and the delta function insertion. And here you have to then solve the scattering equations where you've imposed those same type of Cooper-Nielsen gauge fixing condition on the Riemann sphere. The way it works is that we sum over all the algebraic solutions, so it's a different way of integrating. It's really more like summing. And these equations generally have very complicated solutions. They have n-rows of some polynomial equations. There can be complex momenta, etc. But it does feel like a lot like string theory. So one of the things we were wondering about is how come there's not a kinematic factor in the prescription? I mean, is there supposed to be a Cooper-Nielsen kinematic factor, and can we put it in by hand, for instance? Another thing is that if we put in a kinematic factor like a Cooper-Nielsen, we can immediately see, say, at 4 point, where we have only one variable, that if we start taking derivatives, we get stuff down in front of it that looks like the scattering equations. So it's like the scattering equations are speaking to string theory, but they are not necessarily speaking in the way that we normally want to see string theory, where we have volume integrations, scattering equations like stuff like residues, but they are somehow generated by the Cooper-Nielsen factor. So the simplest scalar dual model one can write down is the following. So basically you put a cyclic factor of this to the minus first times the Cooper-Nielsen factor times this integration here. And the way it works is the complete standard way of doing string theory. You compute this integral with this gauge fixing and the fixed points, and it brings you the amplitude. So we can try to do that at 4 point. So at 4 point, we have to compute this integral here with this factor here. So we, of course, simplify the x. This becomes minus 1. This becomes also minus 1. And then we compute the result of this. This is a standard result. This is the beta function. So it's the gamma alpha s and the gamma alpha prime t and the gamma alpha prime t plus s. We expand in alpha prime. There's a factor of alpha prime outside that comes from the measure. And that gives us immediately 1 over t, 1 over s, 1 over t, plus some alpha prime corrections. So if we truncate here, we have field theory.
So you just understand what you're doing. You're not doing standard string theory. You're just mimicking CHY.
No, this is standard string theory. This is just like what, if you go to a string theory book and you want to compute scalars, this is the formula. And you're just computing.
The last term would be there.
So in string theory, this term would be there, but if you want to make a...
the Park-Taylor part in your string amplitude would be there?
It would sit here. But this is scalars, not gluons. For gluons, the Park-Taylor would sit here with the poles. Or this would be the Park-Taylor, basically.
And on the previous slide, you had on the first line, at the end, you have this product of differences between z's.
So this is Park-Taylor-like, but it's not the Park-Taylor. I mean, it actually goes...
What's the explanation for why you put it there?
I didn't put it there. String theory put it there. Yeah. If we go back to the formula by... Yeah, actually this one. This is the CHY. So you see the cyclic factor is squared, and here's the Cooper-Nielsen, and this is the measure. But now we put in the delta function. This is not string theory. But the other formula, this is if you go to Schiak 73 or something, and he has a pion model, and he says this is like the pi 0. We can compute it like this. You have to do this integration. You have to put this cyclic factor to the minus 1. So it's important that it's minus 1 and not minus 2. Minus 2 is CHY. But you compute, and this is how you compute. And to the leading order, this is what he's interested in. You just get this result. Of course, you want string theory full. You compute all the alpha prime corrections to the higher points. So now we try to do the same in the CHY. So here we see that it's actually a simple expression, our gauge fixed. The cyclic factor is squared. And we solve the equations, so there's 3. They are all dependent, so there's actually 1. And the way it solves is that x has to be s over s plus t. So we rewrite in terms of x, put it in. There's a Jacobian we have to work out, and it's the same result, but without the alpha prime correction. So the CHY doesn't give this alpha prime correction, it just gives the leading result. While string theory gives us the leading result plus the rest. And the measure is completely different. So there's a completely different logic here. It's not the same.
Just to understand this.
Yeah.
This is because of the delta function in CHY?
It's because in string theory, putting in the delta function is unnatural. I mean, in string theory, you would like to integrate over the volume. So putting in the delta function is like putting in equation of motions. But the amazing thing is that you can actually do it and get away with it if your integrand is right. So that's the point. But I'll make it more concrete now because. So we see that in the string theory case or the dual model case, we do an ordered integration along the real line, and all the pole comes from a pinching region. So it's like when the insertion meets a 0 or 1, the integral blows up and you get a pole. In the delta function, there's just this fixed point of the s over s plus t. That's the fixed point. That's not where there's a pinching limit of string theory. And the solution doesn't have to be on the real line. Like s could be infinitely and t could be small. So that would be another point. However, we can write a model that sort of bridges the two. So this is the direct multiplication of the dual model without the delta function, but with the Kuber-Nielsen and the cyclic factor to the -1. We put in the delta function and another cyclic factor to the -1. So it gives us the -2 we want from CHY, the delta function, but now we have a Kuber-Nielsen factor as well, which CHY don't have. So it's quite trivial that it's just a new measure of string theory which puts in the delta function and a cyclic factor. So at finite alpha prime, you can see that you can solve the constraint and you don't get alpha prime corrections that mimic string theory. But you have the two limits where alpha prime goes to 0, which is the field theory, where it matches exactly, or the infinite limit where you meet the Gross-Mendel limit, where it again matches. So you have a bridging model for this. So for scalars, this seems to work. So what about gluons? So the way string theory puts in the polarizations, we've already seen it in the open string expression. So this is a slightly different form. You have the Kuber-Nielsen factor, you have the integration, and you have this exponential where the epsilon sits. And in this form, it's been rewritten so that the part of the supersymmetric, well, this is the bosonic string actually. It should have been supersymmetric. But you can get the Pfaffian structure by just working out these theta integrations. And basically, if you do it right, you get the Pfaffian out. So the expression that you get for gluons from string theory looks like this. So you have the Kuber-Nielsen factor, the Kuber-Nielsen gauge fixing, a Pfaffian, and then you have a correction to that Pfaffian, which comes from string theory, which brings in a lot of these 1 over alpha prime to the k poles, and that's all the tachyons in the theory. So what you have to ensure in order to use this formula for gluons is that the tachyon poles are cancelled with the Pfaffian. So in this Pfaffian sits a term that has to combine with a tachyon. In the Pfaffians, it's a term that looks like it's gluon. It comes, and it has to combine with a tachyon. And the way it combines is the standard way of canceling a pole. So like the tachyon pole is like a s plus 1 pole. And you have to generate in the numerator something like an s plus 1. Once that happens, the tachyon cancels. And that's what this factor here ensures. So now we can really just see the formula of CHY as a string theory where there's an alpha prime correction due to the tachyon. And also for gluons, it's clear that we can go to alpha prime to infinity, and this term goes away because alpha prime goes to infinity, so that's just a Pfaffian. So the CHY result was actually proven without any use of string theory via BCFW recursion by Dolan and Goddard. And we have seen yesterday from Mason and Skinner's talk, and we will hear more tomorrow about a lot of progress in the ambitwistor space at 3 and 1 loop. So the ambitwistor space is not too far-fetched from this string picture. There's some differences. And also you can do stuff in the pure spinor formalism. So one of the features that happens in Mason and Skinner is that you basically have this formula imposed, but you don't have contractions like del x and x, because that gives you stuff like this in string theory. And you also, in string theory, have contractions with two derivatives giving you double poles. So in string theory, these things are crucial. This is what happens to keep all these massive poles working in the string spectrum. But in the twistor string, you don't need this. You've sort of truncated it from the start. So you have a formalism which basically works for the massless fields only. But in string theory, you have to keep track of this. So the main point of doing it in string theory is to sort of show that you can do it. You just have to be more careful in the way you're doing it. And string theory offers another thing that's very nice, that you can basically do any amplitude. So there's no additional complications doing fermions, bosons. You can mix amplitudes. Once you have written down a set of vertex operations in string theory that gives you single poles, you can take that integrand and plug the scattering equations in, and you have results. So you're not bound by a CHY formula that, say, works for gluons, for scalars, and for gravitons. You can actually mix stuff in. And even though you can use these newest results of Cachaso to reduce stuff, I believe you can do the same in the string theory without any additional problems. So the two main ingredients is that one has to get an integrand in string theory that has these simple poles. And once you have that, and that's like canceling these tachyon poles, you impose the delta function prescription and you compute. So the only problem with that is that we have to actually sum over all these integrations. And the integrations in these equations that are given by the scattering equations are n minus 3 factorial. And they are not nicely looking, as Sweet put it the other day. They give a lot of, if you actually solve the setup polynomial, they're really normally just numerical numbers and complex, and you just get very bulky results. So it would be nice to have a much more compact way of doing the integrations. And actually, this is what we've been working on lately. It turns out that it's possible to give some rules. So the way to think about it is that we are just, in this work so far, really doing scalars, but we are thinking about doing gluons as well. So if you look at the scalars, you have one integrand like this, which is this cyclic squared factor. And this can really be diagrammatically thought as a double line between points 1 all the way to n. And in the CHY, the result we know is just the n-point scalar function. So we know that as a set of Feynman trees. So the question is, if we say write it down for 6 point, this is the integrand diagrammatically, can we identify the various terms in this amplitude? I mean, the various Feynman terms. So we have to think about integrands that has arbitrary product of factors in the denominator, and each factor should have weight 4. So in this diagram, we can immediately see it has weight 4 because there's 4 lines coming out of each point. So what we want is diagrams which are made from distorting, say, a diagram like this by taking a line here and moving it somewhere else, but ensuring all the time that the number of connections stays 4. And then there's a rule. So if one has an integration over the CHY measure and you have a well-defined integral, the result is just this product of S poles. And there's two conditions. so for each set we can find, there has to be exactly this number of factors of set I minus set j, including multiplicities in this denominator, that involves pairs of ij that are a subset of Q. And we think of these sets as nested complementary. That just means that we can have a set, say, at 6.2, 3, 4. We can think of that as 5, 6, 1 as well. So if, say, we are asking is 2, 3 a subset of this, we will answer yes. But we will also answer yes to it being a subset of this. So we don't make a difference between this and the complementary set. And as a rule, the easiest thing is just to avoid that one of the legs appears in all the sets. Then you're assured that there's no complementarity issue. So let's do this by example, because then it's much easier. So we have an integrand here. So the integrand here is all the lines that, so there's an edge line, that's the cyclic factor. The one, the product, the Park-Taylor, sort of, so to speak, ij. So that's the rim. And then we multiply by the HF set. That's the integrand, this. And now we just look at the points. So we see that 3 and 4 are connected by a line. So we have 2 variables and 1 connecting factor in the integrand. For 5 and 6, we have 2 variables and 1 connecting factor. For 2, 4, and 3, we have 1 and 2 connecting factors. And for 3, 6, 5, and 4, we have 4 variables and 3 factors. So that means we have 2 sets we can write down. So 3, 4 is a subset here. 5, 6 is a subset of the complementary to 2, 3, 4. Or 3, 4 is a subset, and 5, 6 is a subset of this. But these two are not subsets of each other, because 3, 2, 4, 3, and 4 can't be a subset of 3, 4, 5, and 6. That means that the result of that diagram is this. So the S-pole just follows the sets.
What's the idea of the proof?
I'll come to that. So I decided not to present it, but we have proved it 2 ways. So one way is to go to string theory and just write the integrand down, write the integration down, and find the singular areas in the volume, and that confirms the rule. Or you do it by global residue theorem. So you write down the poles and use the global residue theorem to show that this is how it works through using Dolan-Goddard's methods, for instance. And it always works in these cases.
Do you have insight how the CHY solutions, how they combine perfectly to give you this thing? The solutions are a little obscure.
It's a little obscure. I mean, it is due to the fact that in some sense, this is, I think, from the physics point of view, an unnatural split into these n-3 factorial solutions. So you actually want to consider the sum rather than the individual residues. And the residue theorem is sort of, I think that's how it works in the Dolan-Goddard case, that in some sense you see clusters of residues, and that's the right object to consider, because that gives you the result out right. While if you look at the individual pole, I mean, of course, they have to combine with other poles to be nice. So it's a little bit like, I think when you do loop integrals, you have these unreal poles. Or, I mean, you can make very ugly splits of, say, a box function into various components, and it's only when you combine them that you see something nice. So but in string theory, I mean, it's very straightforward, actually, because there you see the integration regions are exactly where the integral is divergent enough to give you a logarithmic singularity. So I think in a way string theory provides you the answer why it has to be so simple, and the global residue ensures that it collects the n-3 factorial residues. So it makes the link to the CHY.
Can you do the same for everything else?
So I'll come to that. So now we can just do a number of examples. I mean, these are things that are extremely hard to do in the CHY. I mean, for instance, this 10 point. you have to do 10 minus 3 factorial. And I mean, generating the 7-point CHY solution I can do on the computer, but it takes time. If I want to go above 10 points, it's actually very hard. But the rules immediately give it, once you write it down like this, all you have to do is permutations and combinatorics. So for instance, this one is a natural factorization in two 4-point blob vertices of the 6-point. So this is one of the, you could say, one of the Feynman diagrams you could derive in the 6-point amplitude. This one is the Feynman diagram, the Mercedes event that you also put into the 6-point. So, and then the nicest way we come about to see this is actually just to go back to Feynman diagrams and to dress them in a certain way that we call weaving. So say we draw a Feynman diagram like this, and now it's only 3-point vertices. What you do is you put in a double line notation, but every time you meet a propagator, you just have a flip like this. And then you just follow lines. So 2 starts with 2 lines. It goes down to the vertex, and it crosses, and it crosses. So 2 here goes all the way to 6. And 1 here goes all the way to 4. And you just follow crossing the vertices. And once you finish, you just draw the lines like the CHY diagram. And you can immediately, from that, read off the poles, because you know what they are in the Feynman diagram. So you know that's the result of the CHY diagram. So here you have the S pole, the 4-5 pole, the 6-7 pole, and here you have the 3-4-5 pole. And if you want to understand more complicated diagrams, that's possible as well. So this you can write out as this integrand here. Now we can try to do some more complicated examples where once you start having more legs on a vertex than 3, it's nice to use these polygons. So you draw this polygon decomposition first. So each vertex just becomes a gon, and you just follow lines from 9, say, through this vertex to 2. So 9 here goes to 2, and 12 goes all the way through to 5. And you can do examples like this. And you can even see that you can always decompose these gon vertices. So so for instance, this one, this is a blob made up from 2 phi cubed. So this is the 4-point of a phi cubed. So you can decompose it down to the triangles. This you can do in the following way. So you rewrite this one as these 2 triangle decompositions. And that's exactly what you would do had you do a partial fractioning of the integrand. And the proof of the rules, the diagrammatic rules, are actually very simple. All you have to realize that there's a factorization statement, that you can take 2 CHY diagrams and you can merge them on a line. So it's noted L and R. This is this point. And the operation is just you write the diagram like this, where you have these 4 connections exposed. And once you've merged, you end up with this diagram here, where there's a cross. And this is what we call the weaving technique. And now we can write down, this is the 5-point. This is all factorizations of the 8-point with 2 5-points. And this is 3 5-points connected in a CHY sense. And from this, it's trivial actually to do phi p, because now we can just write out the vertices as gon structures, and we just write out the different topologies, and afterwards we sum over the cyclic permutations and dress it up with the double line factors. So this was basically what I wanted to say. So I think it's clear from this that we have much more to learn about the CHY formalism, especially the origin of such relations. And it's interesting that we do not need to know the solution. So I think there's some work to be done still in order to understand this, this connection, but it makes it much more useful way of writing the CHY diagrams once you have realized that you can just write out the result immediately. Because the integrands themselves satisfy a number of beautiful properties, like you can use graph theory arguments to sum them in certain ways and write out factorization limits. And once you realize that you can just basically expand in terms of scalar propagators, you can write out almost any theory you want because you have the building blocks for it. For Yang-Mills, this is Henrik's questions, and also gravity. I mean, you have to introduce the Pfaffian. So you get one factor less from the cyclic, and basically that gives you fewer terms in the denominator. You have some aspects there that you have to consider. So one of the aspects is that you can have diagrams that have, say, a triple line. So this is allowed. This is an allowed diagram because there's 4 lines everywhere. So the integration rule actually doesn't apply directly to this one, but there's a way to compute it anyways. That is that the Pfaffian, if you take a Pfaffian and you multiply it by a certain diagrammatic form, and here you can pick something. You could pick, say, so now we have to be careful to do this right. We could try something like this. So this has 4 lines everywhere. Now we take and multiply the Pfaffian on top of this. So this we can compute. This is bound to give other diagrams that also have 2 lines. It might give some places 2 lines another place. But you can make relations like this one. So this is a very bad triple line diagram. So you rewrite it through a Pfaffian identity into this. So you have a triple line here still and triple line here. And then you continue this decomposition. It feels a bit like, it's like when you do integrations, you can have the need for using IBP relations. This is the CXY equivalent of such relations. But in the examples we've looked at, we can always decompose in some feasible way. So I think the construction we have should immediately extend to gluons and gravitons. So one of the points I wanted to make.
Excuse me?
Yeah.
Sorry, could you just mention one more time where these kinematics, so you explicitly use the CHY Pfaffian, is that right?
Yeah.
Put this in and then use some Pfaffian identities to
So,
define the denominator?
well, the thing is that if you multiply with the full Pfaffian, it's an overdetermined system. You know you have an identity because it has to vanish. So you try to find some way where this diagram could appear by multiplying another diagram times a vanishing Pfaffian. So then you get an identity between diagrams. If one of those diagrams is like this, then you have a relation from this to one of the others. And you have to go through a various set of identities like this to find the right one. So that's like IBPs. When you write down an IBP, it doesn't immediately give you what you want, but you can write another IBP and find a relation between the two. So this should be streamlined, but we have actually resolved for the whole 6-point, written out all the 4-line, triple-line diagrams written in this form.
Okay, thank you.
So we can quantify this picture I showed. So string theory giving us one diagram and a bunch of Feynman diagrams. Now we can write it in this CHY language. So we take the full 6-point, and this is the result in terms of Feynman diagrams. Here's the Mercedes. There's some permutation sum. There's 2 diagrams. These diagrams here are the normal diagrams with 2 legs up, and you have the diagrams with 1 leg opposite. That's those diagrams, and you sum the permutations, you have this. And we can do better than this. We can also do sums of these and use that whenever we have these double line on the edge factorizations, we can do very nice rewritings. So for instance, we can have diagrams like so actually these diagrams are like two squares. So they have a definition in terms of 4 diagrams with triangles. So we can do some summations of diagrams like this in shorter forms. And the shortest form we can write down, that's the one with the double arm around the edge. And in a way, I think in Feynman language, this diagram is what we cannot compute. This is a Feynman diagram that actually doesn't display any preferred factorization. It is really just a 6-point diagram. And that's what string theory naturally gives us. So this is what I had planned to say.
Questions, please?
Well, what do you want to say about loops?
Well, it could be interesting to investigate some of this. We looked some of your string-based rules at loops, because I mean, it looks like a lot of the ingredients are already there in the string-based rules. So the way you do the loops there is that you write down, I mean, we have seen the scattering equations, the tree-level ones, which uses just the worldsheet correlators. And then you have the loop ones, which are quite horrible. But the way you are working with the string-based rules, you're rewriting those as these one-dimensional green functions. So you're mapping, in some sense, the result of string theory into a sum of something you call loops with insertions, and then trees. And the way you compute the trees looks like they're very close to this form. So if one could find a way to dress this up right, I think it might be just feasible to in some sense, make a proof of the string-based rules directly from this perspective. And that would give a direct way to do the loops.
At one loop, with scattering equations,
Yeah.
at one loop, I mean, you could just apply this directly to those scattering equations.
Okay.
Because it just looks like true level.
Okay. I mean, the rules themselves looks a bit cumbersome, this kind of permutation. Actually, from the point of view of computing, it's very neat. So we have code that can compute these horrendous diagrams in no time, because this is just permutations, and Mathematica loves permutations. I mean, it doesn't have to think about topologies of Feynman diagrams and vertex here and stuff. I mean, here you just sum over a different set that satisfy criteria, and once you've summed over all the sets that satisfy the criteria, you have the amplitude. So it's actually, in a way, a much cleaner way of doing Feynman diagrams than traditional ways where you have to define a gauge and stuff like this. Here it's just graph theory. I mean, you just write up what is the different kind of partial fractioning identities you can do, and this gives you the set of relations between the amplitudes.
Let me ask a question. So what's your explanation for why, from the string theory point of view, why amplitude is supported on the solutions of scattering equations?
So it's a good question from string theory point of view. I think it's related to the fact that in string theory, I mean, you're doing basically a volume integration over some integrand. And in the end, you take the result and you take a limit where alpha prime goes to 0. And that gives you the tree or the result you want. Now, the scattering equation offers a perspective where you don't do this volume integration. You're just sort of doing the CHY pole integration. So in some sense, I think it's like taking that limit and putting it underneath the integration sign. But mathematically, how that would work is not so clear. Because here it's very crucial that this you integrate with the alpha prime in it, but you take the limit afterwards, because when you get the poles, they come out like alpha prime s from the pinching. While here it's like a way of seeing the same poles, but without the alpha prime. So it's like a direct way of putting in the limits from the start. And I think when you go to the Gross-Mendel limit, it's very clear that there has to be a connection like this, because there the volume integration just pinches out and becomes like there's a parabola solution. In this limit, there's none. So the scattering equations are sort of unnatural from the trivial point of view. There's no fixed point that tells you to do this. But it's like the symmetry of the high energy solution is preserved in string theory and allows us to do the same operation at tree level. I think it's very close to what David said in his talk at Amplitudes. But it could be interesting if there's some kind of more specific or definite mathematical way of taking this volume integral and rewriting that limiting directly. I think that is a very nice problem to work out. And I think the elements are almost there in the sense of stuff like...
Would it be possible to find it alpha prime on the same levels?
I think it would give us a handle on, or a better handle on doing finite alpha prime. So I think maybe the delta function is a very crude way of imposing this, but you could maybe think about some kind of generalized function there, maybe some kind of limiting Gaussian or something that would allow us better to probe alpha prime corrections.
So you had formulae that were supported on the scattering equations
Yeah.
of finite alpha prime. I mean, that's not string theory, is it?
It's not string theory, no.
I mean, do you know what?
We don't.
Is it anything that you could argue?
I mean, we don't know what it is. It has nice properties, actually. I mean, it has some kind of a BCJ. I mean, you can write, you can take like these S over T relations. You can have things that has this to the alpha prime, some factor. So when alpha prime goes to 0, it's like something like this. So when alpha prime is 0, this is just the normal relations between 4-point orderings. But when alpha prime is non-zero, you get some kind of new BCJ-like ordering that has an alpha prime, like these factors appear. But it's very unlike the way that monodromy works, because there it actually makes this an exponential. So it's a funny version of, I think, maybe regulated tree string theory. I mean, it feels much more like a tree theory that is just sort of deformed in some way than a real string theory. I mean, it lacks all the massive modes and things like that. I mean, but question is, could you have that in if, say, the delta function is maybe not as sharp as a delta function or a broader function? I think the answer is possibly yes, but it would require some mathematical work. Another question I think is interesting is this Pfaffian that appears in the integration. I mean, is this some kind of generalized statement? I mean, Stokes theorems, it almost feels like this is like a version of Gauss theorem. Like you have a volume integral and you write it as a smaller integral where you sum over some poles or something like that. I mean, is there a version of that would allow us to take directly string theory volume integrals into integrals that are, say, more like CHY-like directly? I mean, some kind of general... I mean, the Pfaffian seems to be on the right track, but I mean, it's just a hand-waving thing.
It looks like it should be a change of variables.
Yeah.
But it's not.
Yeah.
Just be able to make that precise.
Yeah. But the Pfaffian, on the other hand, I mean, you write down the Koppe-Nielsen factor. That sits here. I mean, the Pfaffian really is just when you expand this and you expand the string theory, it comes out immediately. I mean, there's no, it's not a very spectacular object from the point of view of string theory. So it is very natural to have a Pfaffian in string theory, and from that perspective, it's interesting that. But I think people realized it, but they just call it something else, like Bersin integral or something. I mean, it's not like they have called it a Pfaffian.
And also the other, I mean, sorry, does the Gross-Mendel limit actually give you? So you get the scattering equations back at alpha prime equals infinity.
Yeah.
Are you actually getting tree amplitudes back again?
No. So in the gross Mendel,
what's the distinction there?
so the distinction is in the gross Mendel limit, you do this, you get the strong coupled field theory. So you get something.
Right, but you've still got a formula with some tachyon there, or is something disappearing?
You have a saddle point approximation, right? So you have the exponential still there.
Oh, the exponential is still there. Is that the point? Okay.
Yeah. I mean,
Just the leading contribution, just the leading point.
Oh, okay, I have just one solution that contribute to it.
Oh, sorry, if alpha prime is infinity, is the what is it you're getting there? The very. Yeah, sorry, I'm making take it offline. I never thought about that actually.
I think the closest thing is actually if you take this paper by Alde and Maldacena, where they look at some area integrations in strongly coupled string theory, is very alike to the way that you get the scattering equations coming out in the gross Mendel limit. I mean, if you look at this paper by David Fairley back in '72, it's almost there. He rewrites the constraint that is put in by the scattering equation as some kind of area constraint. And although he has no interpretation of what this would mean, it is a geometric constraint alike the one that you have a minimal area for your scattering amplitudes like Alde and Maldacena. So I think there's a connection there to be dug out at strong coupling. But I don't know if that will lead us to some conclusion at tree level. I think at tree level, it needs something additional. It's a very curious thing. But one hint is maybe that the integration you're doing in string theory seems to be, I mean, the alpha prime, you're taking it to 0. So the integral that you have afterwards should not depend on alpha prime. And the same way when you go to the gross Mendel limit, alpha prime is going to infinity. So the integration should not depend on alpha prime. So from that perspective, at the tree level, the results should be alpha prime dependent. And that would favor a CHY prescription that doesn't use an alpha prime. So maybe there's some way of regulating that story.
Should move on. Let's thank him again. A few minutes break.